Good morning, and today we are going to introduce the concept of linear regression. So I'm going to clean our studio session. Today's code is already in place. We're going to use, first of all, two of our libraries, dplyr and ggplot2, both of which we've seen before. I'm going to load a data set of blood sugar readings from a study of children. If we look at these data, we'll see that they contain an ID number, a month, a day, and a year, an age, a blood sugar reading, height, and weight. And so for the purposes of today, we're not interested in the diabetes piece of this. We're going to, as an illustration of linear regression, we're going to relate age to height. Okay, and we think there probably should be a pretty strong relationship here because the older you are, the taller you are among children. And so we will investigate whether that is true in these data. First of all, however, I am going to make a plot of the data, and I'm going to use ggplot, and I'm just going to run the first two lines of my ggplot statement for the moment. Ggplot, our data is diabetes. Our aesthetic, which is where we tell ggplot what we're plotting. So our x-axis, we're going to show age in years, our y-axis height in centimeters, and we are going to depict the data as geometric points. Okay, so if I just run this portion of ggplot, we see something very strange. Age in years on the x-axis, height on the y-axis, and so it looks like we have a whole bunch of heights that are at about 1,000, and all the other heights look like they're in the normal human range. So what's happening here is our familiar problem where someone has used 999 to indicate missing data, which is something that we should never do, but people do it, so we have to look for it. And so the first thing we have to do is filter those out so we get something that makes more sense. So I'm going to add this line of code here. So our diabetes data set, I'm going to filter it where the values are, actually this is not typed correctly. I'm going to filter diabetes where the height in centimeters is less than 999. Okay, I run that, and we see that our number of observations has gone from 910 down to 892. And if we run our ggplot statement again, just the first two lines. Okay, we now have something that makes more sense. Age goes from, it appears, 9 through almost 16, and heights go from just above 120 centimeters to nearly 190. Okay, so that all makes sense. And it looks like there is a relationship here, right? Definitely as age goes up, the height goes up. And obviously these data are noisy. There are exceptions to the rule. There are examples of tall 9-year-olds and short 15-year-olds. But for the most part, we have a relationship. And it looks like this relationship could be described by a straight line. And so that's what we call linear regression. And so here is the key statement. I'm creating a variable called regression, and I'm assigning that the function LM, which stands for linear model. And in my linear model, I want the height. So I want the y-axis value, in this case the height, to be a function of age in years. And we use this character called a tilde to indicate the relationships in a regression model. There's a few other places where R uses this too. So you have to remember to use this character and not any other character when executing the LM function. Okay, and then we tell it that our data set in this case is diabetes, and we execute that statement, and we see now we have a new data item called regression, which is a list of 12. A list is a data structure within R that is pretty complicated, but that lends itself to the summary function. So if we do a summary of regression, we get a fairly compact summary of the relationship between age and height. Okay, so we'll look at this, and some of these items we will not talk about today. We'll cover them later. Others we'll talk about now. So starting off, it gives us back the formula that we entered. It then gives us residuals, which we will not talk about today. And then we move on to coefficients. And so these are the values that can be used to define the straight line that best fits these data. And the way we interpret these coefficients is we look in the estimate column, and the intercept is a constant value. And so we would say that the relationship between height and age is equal to this constant, 75.9, plus this multiplier times the age. Okay, so the linear equation, and I'll type it down here in the console. We're going to say that the height in centimeters is equal to 75.9464 plus 6.2634 times age in years. Okay, so that's how you interpret these results. We also get a standard error around these estimates. Okay, so these are not exact quantities. This is the best fit, and we'll explore the standard error in more detail in the future, but this gives you a sense of how precise these values are. We have our old friend, the t-test, and you can calculate a t-score based on the idea that any of these coefficients are different than 0. So obviously with numbers as high as 75.9 and 6.26, we can be strongly suspicious that these values are above 0, and we have very big t-scores. And then we have a p-value, which is given here, and the p-value is 2 times 10 to the negative 16th, which is an extremely tiny number, and in fact is the lowest number that R will report. You see, it actually tells us that it's less than this. Okay, and so remember, the value that we typically look for is 0.05, and so this is vastly below 0.05, so this is highly significant. We have a very strong relationship and a very strong finding that these parameters are different than 0. Another reference to residuals, which we'll talk about in the future, but I do want to talk about this concept called R squared. And so we have a multiple R squared and an adjusted R squared, and you'll see that they are nearly identical, 0.6943 and 0.694. I'll talk a little bit about the difference between these two concepts, but for when you have large data sets, their difference is negligible. So this is another one of those little adjustments that are made when your sample sizes are small to get something that is hopefully a little more accurate. But for large samples like we have here with 892 observations, the differences are negligible. So what R squared is it's a measurement of the quality of the fitness of the relationship. The range goes from 0, meaning there's no relationship, to 1, which is a perfect relationship. And we can interpret values between 0 and 1 literally to mean what they say, so in this case 0.694, means that 69.4% of the variation in the heights of children in these data are explained by their age. Okay, that means there are still a little over 30% of the variation are explained by other factors. But the majority, a large majority of the association is explained by age. And so, again, this is evidence of a strong relationship. It varies by field, but in public health, working with human subjects data most of the time, it's fairly typical to see R-squared values of maybe 0.2, 0.3 for a lot of things that we look at. So 0.69 is quite high. And that's because we're studying, in this case, something that's very obvious, which is the relationship between height and age. Okay, and then we have some information on an F statistic, which I won't talk about. But you can see that from this output, we see a lot of the concepts that we have already learned about. Okay, so we are really tying things together. Linear regression is sort of the capstone of this course. And so a lot of what was building up to this point were the necessary building blocks to be able to understand this. Okay, so since I've talked about how a straight line describes the relationship between height and age in these data, we can actually plot that straight line. And we do that by adding one line to our ggplot statement, which is the stat smooth function. Okay, so it will draw a smooth line using the method of our choice. In our case, our method is linear model. And just to make it more visible, I'm specifying the color to be red. So if we execute this statement, okay, so we now see what the best fit line through these data to describe the relationship between height and age looks like. And so one useful thing about this line is that if you choose any point along the line, it corresponds to the values from these coefficients. So for example, if we want to find what is the predicted height for someone who's exactly 10 years old, we plug in 10 into this formula. I'll type it into the console here. Okay, so now we have 75. I'll round off. So now we have 6.26 times 10. So we now have 76 plus 63 rounded off, 139 centimeters. And if you look over on the graph and you look at where the age is 10 and you go up to where the red line meets that value, you'll see that we are at 139, approximately 139 centimeters. Okay, and that is all for today. This is just meant to be an introduction. We'll be going into this in a lot more depth in the days ahead.